Well, now that we have seen that dictionary learning is of interest and importance, let's turn to define this problem clearly. The dictionary learning problem starts with the accumulation of signals to train on. Suppose that we have access to n such examples believed to emerge from SparseLand. More specifically, each of these signals is expected to have a K0 sparse representation with respect to the unknown dictionary. Furthermore, being rational, we shall assume that these signals are not perfect, implying that we expect an epsilon deviation from the model posed as additive noise. The learning process will use these signals and several parameters that we assume as known and seek the best fitted dictionary. These parameters we may use are K0, the number of non-zeros in the representations, epsilon, the representation error, and m, the number of atoms we assume D has. In fact, when learning D, we will also seek the signal's representations, alpha j. Thus, our goal would be to get both D and the representations to match the model assumptions we have just posed, K0 sparsity and epsilon representation error. Let's formulate our task as an optimization problem. The following are two popular options. The first searches for the smallest average sparsity while constraining an epsilon representation error. The second flips the roles between the penalty and the constraint, minimizing the average representation error while forcing a fixed cardinality on the signals. The choice between the two depends on the knowledge available to us, whether epsilon or K0 are truly known. Let's have a closer look at this problem by focusing on the second option. Could we claim that this problem necessarily leads to a unique solution? The answer is unfortunately negative. First, observe that the order of the atoms in D plays no role, and thus any permuted version of the same dictionary will lead to the same quality estimate. Secondly, since both D and the representations are unknowns and they multiply each other, there is a scale ambiguity between the two. A remedy to this second flaw is to force the norms of the columns in D to have a unit L2 norm. Here is an interesting question. Suppose that we are given such a set of training signals emerging from SparseLand with the parameters D, K0, and epsilon. Could we guarantee that the original dictionary D is the only way to sparsely explain this data? Surprisingly, this question has been addressed in the literature only for the noiseless case. The work by Aharon has shown that indeed, if epsilon is 0, then D is the unique solution up to permutations. We will not dive into the conditions for this to hold true, but simply mention that K0 must be small and n, the number of examples, must be huge. What about the noisy case? Could we claim some sort of stability? I believe that this is possible, but this has not been studied yet. Here is an interpretation of the dictionary learning task which may be found more intuitive. Assume that we gather all the signals as the columns of one big matrix Y. Similarly, we gather all the representations alpha j as columns of the matrix A. Then our goal is in fact a matrix factorization. We are given Y, and our goal is to find a decomposition of it as D times A, where D is of known size and has normalized columns, and A has K0 sparse columns. The factorization should be done such that Y is as close as possible to D times A. Notice that our quadratic expression uses the Frobenius norm, as we measure the distance, the L2 distance, between two matrices. This norm simply sums the squares of all the differences. Another helpful interpretation of dictionary learning emerges when we consider a very specific special case. Suppose that K0 is set to be 1, that is, we allow each signal to be represented by one atom only. Suppose that we further constrain the problem by demanding that the non-zero multiplying this atom should be 1 as well. This means that in our representations of signals, each example is simply represented as one of the atoms in the dictionary as is. What are we looking at here? This is the well-known clustering problem, which gets a set of n examples and divides them into m concentrated groups. Here is an illustration of this clustering problem. We have these points in our n, and our goal is to divide them into m groups. This is the energy we are minimizing. Per each example, we assign the closest atom, And for all this set, we ask what are these best atoms. So if these are the identified clusters, then the best atoms would be the centers of mass of each of the groups. By the way, you may get the impression that clustering is an easy task, judging by the clearly seen grouping in this example. Remember that in the general Rn case, visualization is impossible, and we operate in the dark to find the representative centers dk. So how do we find these centers dk? A well-known and very effective algorithm is k-means. This algorithm iterates between updating the group assignments and the update of D. Fixing the centers dk, we can simply assign each example to its closest atom. And fixing these assignments, we can update each dk to be the center of mass of the elements belonging to this group. This center of mass is nothing but the mean, which explains the name of this algorithm. So as we have just seen, clustering is a special case of the dictionary learning problem. The k-means algorithm, which manages the clustering task, starts by choosing an arbitrary dictionary D as initialization, and then iterates between a nearest neighbor computation for each example, followed by a mean computation per each group. Iterating this process several times gives a descent in the objective functions, but this is not guaranteed to get to the globally best solution. Nevertheless, this algorithm is known to perform very well. And our question now is whether we could suggest something similar that treats the generalized task of dictionary learning. The answer, as you may have expected, is positive. In fact, we will suggest the same architecture. D will be initialized somehow, and then we will iterate between two steps. In the sparse coding stage, we fix D and find the alphas. This parallels the nearest neighbor process in the k-means, but it will be somewhat more involved, since now each signal is assigned to k0 atoms and not just one. When these alphas are set, we will turn to update D to better serve the data. These two steps should be repeated again and again, leading to the proposed conceptual dictionary learning method. As we will see next, the above core idea could be interpreted in several different ways, leading to several variations of dictionary learning.